Welcome to the next lecture of CT509. Okay, so I will begin right away. So we started talking about this topic of NOMA last time, and we are going to continue on that today. If you recall, last time we looked at these various multiple access schemes, and we saw how they look like in spectral domain. And we said that the main idea of NOMA is that we combine the successive interference cancellation with the channel coding. And in addition, if the transmitter knows these power levels, power of signal and power of noise as it is received at the receiver, then it can calculate, it can kind of throttle its data stream, data rate that it is sending to the receiver. And this is the famous theorem of information theory that if the transmitter sends the data at this rate, then the receiver can decode it with near zero probability of errors. And so the biggest challenge of SIC, which is that if the stronger users are decoded with bit errors, then those bit errors propagate and they kind of mess up the interference cancellation. That biggest drawback of SIC is addressed. And so SIC works, at least in this ideal case, as desired. And so subsequently we can just say what data rate would be achieved, or in terms of normalized data rate or spectral efficiency, what type of BPCU will be achieved. Now, last time we looked at the return link. Today we are going to look at the forward link. And in NOMA, the return link and the forward link analysis differs in a substantial manner. So we have to be careful when we are talking about the return link and when we are talking about the forward link, because the analysis are quite different. But ultimately, we said that for NOMA, what type of data rate one user will be able to achieve? The user which sees the full interference. And then what type of data rate the other user is going to be able to achieve, given that this other user, let's say the weaker user, is going to first completely remove the interference from the stronger user. Now, again, the key point here is that the receiver has leveraged the channel coding to its most highest efficiency, and the receiver is performing according to this Shannon theoretical bound. If you don't leverage channel coding, then this bound will be probably very difficult to achieve. So that is something to keep in mind, that almost always with NOMA, the underlying assumption is that somehow using some smart channel coding scheme, or a scheme that smartly combines both channel coding and modulation, the receiver is able to operate very close to this information theoretic bound. And so with that, we looked at several case studies, all of which show that the non-orthogonal multiple access performs better than, definitely better than CDMA, especially when the user power levels are imbalanced, but also it performs better than even the orthogonal multiple access. And in fact, we saw that the CDMA paradigm, which is to do power control, was completely turned 180-degree upside down. And NOMA says that I will actually not do power control. In fact, if the two users have different channel conditions, so that one user signal is received strongly at the base station on the return link and the other user signal is received weakly, then that actually is helpful. So go and tell that to a large number of engineers and research scientists in the 1990s and early 2000s who spent a lot of time doing the power control on CDMA, and they were operating at this rad square. So that way, the research community has kind of realized that that was probably a mistake. No doubt we will have to spend more computational resources to operate at one of these vertices of this diagram using NOMA. We'll have to combine the SIC with channel coding and so on. But these days, the base station on the return link can possibly have those type of computational resources. And so then instead of doing power control with CDMA, not doing power control and using NOMA is actually better. Okay, so that is the main lesson that we kind of discussed in last lecture. Now let us look at some of the similar analysis that is possible for the forward link. Now there are little subtleties also here, so let us see if I am able to spend enough time on some of the detailed aspects of the forward link analysis. And so let us move forward with forward link analysis, so to speak. Again, some of the initial presentation slides on this topic are taken from the material which is in that wireless communication book by David Sayre and Vishwanathan. But then some of the more detailed discussions are taken from several papers which appeared in maybe 3 to 5 years back. Okay. So first of all, we'll be again applying the same two-user analytical model that we have looked at on the return link. The same thing we are going to do for the forward link. Now remember, in return link, we looked at 3 techniques. CDMA with SUMF, and then we looked at orthogonal multiple access, and then we compared those 2 techniques with NOMA. On the forward link, we are not going to look at CDMA separately. And one reason is that CDMA on the forward link is sort of like OMA only. So why is that? Well, if you assume certain simplicity in the system model, specifically if you assume that at the user terminal on the forward link, the interference from the adjacent cells is not present. So let us make that assumption. Then you see that on the forward link, actually CDMA can do orthogonal signature sequences. When you are doing these computer experiments, the signature sequences, those 8 chip long 6 signature sequences that you have generated for different users have been arbitrarily generated. And when you generate arbitrarily, you cannot guarantee orthogonality among these signature sequences. But there are ways to generate a binary sequence of length 8 chips, where all of those 8 sequences are orthogonal to each other. And so that type of sequence set will ensure that different users remain orthogonal. And we have seen earlier that if you can guarantee orthogonality, nothing like that. Instead of CT509, you go back to CT516, where everything is very simple, and you gain optimality. So that is possible on the forward link. You may ask that if it is possible on the forward link, why it is not possible on the return link? Well, on the return link, the problem is that the different user signals arrive at the base station with different delays. And in addition, if the terminals are moving, they may have different Doppler offsets also. And in addition, if there is channel impairments, maybe different users have different fading scenarios, then those channel impairments are also going to be different, simply because these different terminals may be coming from different areas. They are not co-located. Now, if you come up with some orthogonal sequences for different terminals on the return link, but then if you start introducing different delays, different Doppler offsets, different Rayleigh fading factors, and so on, then even though originally those sequences are orthogonal, by the time they reach the base station on the return link, the orthogonality is gone. For example, if you use Hadamard sequences, they are orthogonal only if they are synchronized. But if they have time offsets between them, then no, you don't have orthogonality anymore. You may ask that, then why does it work on the forward link? Well, you see, on the forward link, yes, different users are still non-co-located, but the transmitter is common. All the signals for different users get transmitted by the same base station. And therefore, if the base station synchronizes their transmission, then that synchronicity remains. At each user, it will just see the synchronous set of signals. And therefore, if you can preserve synchronicity, meaning that across different users, there are no relative delay offset or Doppler offset and so on, then you can maintain orthogonality, and therefore CDMA kind of boils down to just orthogonal multiple access. Okay, so that is a little bit of a long story about why we will not be looking at CDMA separately. Now, the other difference compared to the return link is that we are going to assume that the transmitter, the base station, has a total transmit power constraint. And this is a very practical limitation that we have to obey. And so that total transmit power of the base station we are going to denote as PTX. And we are going to say that different users are going to take different chunks of this PTX. And those power allocation factors are denoted by beta symbol. So mth user will get beta m times PTX power. And so obviously beta values cannot be greater than 1. If you make any beta greater than 1, it means that that user is transmitting at a power which is even greater than what the base station can transmit. So beta will be between 0 and 1. And we will assume that the summation of beta values is 1. You can make summation of beta to be less than 1, but then it means that you are not utilizing all the transmit power. On the return link, obviously, we didn't do this because different user devices are operating independently. There is no common power constraint there. Okay. Then we will say that the channel from the base station to the mth user has a gain of hm squared. Hm is the channel coefficient for the mth user. And we will say that suppose if beta m is 1, meaning the full power of the base station is devoted to mth user, then that user will get an SNR of gamma m, which is h of m squared times ptx divided by pn. This hm squared times ptx is obviously the received power at user m. Therefore, this is the SNR. Now, in reality, that mth user will get SNR of this gamma m times beta m, because beta m will be some value not necessarily equal to 1. Now, one thing that you will have to note here is that that is the SNR, beta m times gamma m is the SNR that user m gets. But this transmission is also going to some other user as well. And at that user's receiver, this nth user will be received at this power level. Beta m times ptx is the power at which the sender transmitted the signal, and h of k squared is kth user's channel gain. Okay? So as an example, for user 1, the received powers will be h1 squared beta 1p and h1 squared beta 2p. h1 squared is user 1's path loss, and beta 1 and beta 2 are the power scaling factors at the base station for the two users. At user 2, it will be h2 squared instead of h1 squared. So this is also different. Here we are actually talking about 4 different power levels. On the return link, we don't have to consider this additional detail, because each user transmits a certain power and then that user signal gets received at the base station after some path loss. There is no, what would I say, the crosstalk among different user devices. Okay. So let us now consider first the NOMA, then we'll consider the OMA. We'll say that user 1 is far away from the base station, user 2 is closer. Okay. In this analysis, even suppose one time we may actually consider more than 2 users, then you have to remember that user 1 is the weakest user. User 1 is the one who is the farthest away. And user 2 is the stronger user. He's a closer person. If there are multiple users, then they are ordered such that 1 is the weakest, 2 is the next weakest, 3 is the next weakest. And if there are capital M users, then mth user is the strongest user. Now, the strategy with the NOMA is that, first of all, we will assume that the base station knows what each user path loss coefficient is, those HM values are. So knowing that, the strategy that base station will employ is to put greater power for user 1, the user which is weaker. Why is that? Because, well, user 1 has high path loss, he is the farthest away from the base station. And so base station should actually put more power for that user so that the signal reaches that user. Okay? Now, we will see that this is different from what information theory says. Information theory, whose math we are not going to get into, says after some mathematical derivation that instead of doing this, we should be doing exactly the opposite. We should be allocating more power to the user whose channel is stronger. Meaning that the user who is closer to the base station should be assigned greater power. And that is called the water filling strategy. Why does information theory say that? Well, because if you have limited power and if you have a user whose channel is strong, then putting more power resource for that strong user is going to be beneficial because that user will be able to get a pretty good data rate. For the second user, user 1, who is farther away, what will happen? I'll pick up some numbers. Let's say for user 1, you need to put only 1 watt to get 100 megabits per second. For user 2, maybe you need to put 20 watts. But even after putting 20 watts, maybe you will get only 10 megabits per second. So if you have a limited power, and if your objective as a system designer, if your objective is to maximize the overall data rate that the system can achieve in the entire cellular system, then you would actually want to put more power for the users who are closer to the base station, because by doing so you will get you'll be getting bigger bang for the buck. Maybe that is the way to put it. What is the other analogy I can think of? Suppose you are the owner of a horse stable, and maybe you have 10 horses, and you want all those horses to participate in a horse race, but you have limited food. Now, given your budget constraint, which horse would you want to feed the best way? Well, you would say that I will feed my strongest horses the best meal, because they are most likely to win the race for me. I mean, that is the businessman's mindset, so to speak. And so this waterfalling strategy, the information theoretic argument, is the argument of a businessman, that I want to maximize, and so I will give advantage to the users who are already advantaged in terms of channel condition. In contrast, NOMAS takes exactly the opposite viewpoint. that I am going to emphasize on the fairness. If I, yes, fine, I may suffer a little bit in terms of overall system performance, but I'm going to look at what I will do for the weaker user. I don't want the weaker guy to suffer. And so I'm going to give more power to the weaker user. Although it hurts me overall, for the weaker user, that weaker user is going to be the user at the edge of the cell is going to be happy because I'm giving it more power. So there is a little bit of a paradigm shift that NOMA with SIC has compared to what is the accepted theoretical argument of information theory. Maybe I should have some visualization for this. Yeah. So this is the waterfalling strategy. Okay. What is this diagram? See, there are multiple bars. Think of each bar as a user. So there are 8 users, similar to what you are doing in the lab. We are going to assume that these 8 users are at different distances from the base station. And let us say this user over here, the 4th user, is the closest to the base station. And so its channel is the strongest. And therefore, in a nominal sense, the signal to noise ratio at that user is the highest, or alternatively, if I take 1 over signal to noise ratio, I get the smallest noise floor. And so this red bar is the smallest for that user. Then maybe the 7th user is the next closest to the base station. So is the second strongest user, and so on. And then this guy is the weakest guy. This is the second weakest guy. What information theory says is that think of the levels of these red bars as forming some sort of a bucket, a strange bucket whose bottom is a little weird, but it is like this. Or you can think of it as a swimming pool or something with different floor heights. And now let's say you have certain amount of water in the water tank and you start filling up the water. Then obviously the water will get first filled up at this level. And then it will go to this level and so on. And eventually when your entire water tank is empty, you will have filled up this portion of the bucket with the most amount of water. So that is the water filling strategy of the information theory. The NOMA strategy is exactly the opposite. Okay, so that is one thing that I wanted to highlight. Now, remember in the SIC, you always want to decode the stronger user first, and then you go to the weaker user and so on. And therefore, on the forward link, we will say to user 1 that your user 2 signal is going to be weaker, so don't worry about cancelling it out, because user 2 signal is powered less. And so user 1 will just do the SUMF and it will get this type of data rate. What are these notations? PRX11 and PRX21. We have actually already defined those notations earlier. PRX11 is the power of user 1 signal received at user 1. And PRX21 is the power of user 2 signal received at user 1. And remember, this power differential is maintained. Beta 1 and beta 2 is set by the base station. And it doesn't matter whether we are looking at user 1 or user 2. The relative power differential will always be beta 1 and beta 2. The difference will be this H1. For user 1, the received power will get multiplied by H1 squared. If you are looking at user 2, it will get multiplied by H2 squared. And so now that user 2 signal has been attenuated, it is given less power by the base station. Beta 2 is smaller. Therefore, user 1 is asked to treat user 2 signal as interference. So this is something that you should absorb, okay? Remember, user 1 is the weaker user, okay? So you may think that user 1 is the weaker user, and so actually SIC should first decode user 2 and then remove user 2 interference from user 1. But no, that is not the answer. User 1 is weaker, but at the location of user 1, it doesn't matter that it is weaker. What matters is this beta 1 and beta 2 factors. And the transmitter following this fairness policy has made beta 1 greater than beta 2. And so therefore, user 1 is asked to treat user 2 signal as interference and just perform the SUMF. And so its data rate can be written in any one of these three equivalent manners. Now user 2, remember it is stronger user, but the signal that it gets, in that signal, its own component is going to be weaker because beta 2 is smaller. And so therefore, user 2 is asked to perform SIC by removing the stronger component, which is of user 1. When we say this user 1 signal is stronger, we don't mean that user 1 is closer to the base station. User 1 is actually farther away from the base station. But the signal that is received at user 2, in that signal, the component of user 1 is stronger. And so that is what the user 2 does. And so resultingly, it gets R2 given by this formula. Okay, does it make sense? Who should I ask? Divya, are you okay with what is on this slide?
Yes, sir.
Okay. If one of you have any difficulty, Anudeep is your TA for this topic, okay? Anudeep is the expert. He knows this inside out. So you can, if you have some discussion that you want to make informally, Anudeep can help you out. Okay, so moving right on. So this is how the situation looks like. I have actually copy-pasted this figure from one of the references. that were listed earlier. Remember, user 1 is always going to be farther away. The index indicates where the user is located. When the index is smaller, that user is far. When index is larger, that user is closer. And so user 1 actually does this SUMF. User 2 sees user 1 signal as being very strong, as it is shown in this diagram. And then it performs SIC on user 1, and then because of that, it gets its own signal interference free. So this is called the power domain NOMA. And this is where the near-far effect that we have talked about earlier in the context of SUMF, where we saw that near-far can be pretty detrimental for the SUMF scheme at CDMA. Here, that is actually being leveraged, and it is being put to the system benefit. Okay, so this particular strategy of power domain NOMA is at the modulation level, it is called superposition coding. Why is that? Because, see, both these user signals are being transmitted by the base station. And so you would think that, one way by which the base station could have done this is simply treat the user bits in a unified manner. Why does it have to differentiate that this is user 1 and this is user 2? Right? It can just merge both the user bits and come up with a single bit stream, and that single bit stream is what gets channel encoded, and then it gets modulated, and then it gets transmitted. That is what goes back to our CT516. In CT516, we only had single bit stream, which is known as point-to-point links. There's one transmitter and one receiver. Here we have one transmitter, base station, and two users. But both the user signals are being sent by the same base station. So base station can actually not differentiate between the two user stream, and it will just send a combined stream. And then we know that the situation is back to CT516, where everything is ideal. The channel coding will work as intended, modulation will do its job, and you will get the optimal performance. That is, if not in the exact detail the way I mentioned it, something like that is actually being considered. There is a NOMA strategy called bit division multiplexing, which actually kind of does that. Let us see, should I bring bit division multiplexing now or later? Okay, for the sake of continuity, let us move on. We will talk about bit division multiplexing, BDM, later on. But this strategy where the user signals are not processed by the base station in a unified manner is the one that is being adopted here. But still, although these two different user bit streams are channel encoded and then modulated separately, they ultimately do get superimposed on each other. That is what power domain NOMA is. It just merges the two symbols. And the way it does that is pretty much kind of dump one symbol on the top of another. There is nothing else being done. It's kind of as simple as it can get. The name given is superposition coding, but superposition is nothing but taking one symbol and adding it in the complex plane directly on the top of the other symbol. So if this user signals are QPSK modulated, the net transmitted symbol will be the QPSK symbol of first user vectorially added with QPSK symbol of the second user. And so you will get a strange looking constellation with 16 symbols, and that constellation will be separated out in 4 different parts. Each part will look like a QPSK centered at another QPSK constellation symbol. So that is how the superposition coding looks like. I should have drawn a diagram.
So can you repeat the last line?
Yeah, so that's what I'm saying. Maybe a diagram should have helped. Let me try to draw it. Okay, so this is the complex plane, and I'm going to put the QPSK symbol of user 1. Remember, user 1 is given greater power, and so I'm going to put user 1 symbol like this. This is the standard QPSK constellation for user 1. User 2 is going to be superimposed on user 1, and we are assuming that user 2 is also QPSK modulated, but it is given smaller power. And so the user 2 constellation, actually QPSK constellation of user 2 is going to be like this. So this is user 2 constellation because beta 2 is smaller than beta 1. Right? So blue is user 1, green is user 2. But each of these blue and green symbols occur independently because these are 2 different users. So their transmissions are happening independently. And so what gets transmitted out, the actual symbols that get transmitted out, they look like this. right? So blue is user 1, green is user 2, and black is the superposition coded transmitted symbols, which is just the vectorial summation of blue and green. Does it make sense? Okay, are you able to hear me?
Yes, sir.
Okay, that is what the superposition coding is. So in that context is what I was saying is that we don't have to actually necessarily use this strange looking constellation. We need essentially 16 points on constellation, and maybe we can use 16-ary quam. And then we put 16-ary quam carries 4 bits per symbol. And then those out of those 4 bits, we say 2 bits are for user 1 and 2 bits are for user 2, right? I mean, that would be another strategy. And something like that is what BDM does. Okay, so let us look at OMA. So in OMA, the bandwidth, first of all, is allocated using those alpha variables. Remember, we use alpha variables to denote the proportion of the total bandwidth that OMA allocates to different users. Now, on the forward link, it turns out that you probably want to allocate the bandwidth in the same ratio that you allocate the power levels. So alphas become same as betas. So beta here is the bandwidth allocation. And that same beta appears in the denominator for the noise as well, as we saw last time. But this PRX11 also has beta, remember. PRX11 is beta 1 times PTX times H1 for user 1 and H2 for user 2. And so what happens is beta 1 in the denominator, which is for the bandwidth part, but because it is made same as the beta 1 for the power allocation, and we are not doing it here, but we can show that that is the right thing to do. It cancels out, and so you just get gamma 1 in the bracket. What is gamma 1? Who can tell me? What is gamma 1? Joel?
SNR for the user.
Yeah, SNR for user 1, but it is the maximum possible SNR for user 1. Right? We said that it is SNR for user 1 when the base station gives all of its power to user 1. So what is happening is that user 1 is obviously not getting the full power of the transmitter. It's getting only beta 1 portion of it. But still it sees an SNR which is the best possible SNR it can get. Why is that? Because we divided the bandwidth in the same proportion as the power. So yes, the user 1 got allocated smaller power, but then it also got allocated correspondingly smaller amount of bandwidth, and so the receiver sees smaller noise power as a result by the same factor. And so user 1 receiver sees the the highest possible SNR. Does it make sense, Joel?
Yes, sir.
But this, I think we said last time also, that OMA gives you benefit inside the bracket of logarithm. But the problem is that that benefit gets attenuated because this logarithm is a decreasing function of its argument. The bigger problem is that it gets penalized by a linear scalar beta 1, which is outside of the logarithm. And this linear attenuation is more damaging. On the other hand, the benefit is that the receiver design is simplified because it doesn't have to perform any interference cancellation. Now, similar to what we did for the forward link, I can draw the capacity diagrams. If the two users are equal distant from the base station, then either NOMA or OMA are fine. They both give the same performance as it is shown here. But as the users become separated out in terms of power levels, then you start having a situation where blue is always better than green. NOMA outperforms OMA. When the user power levels are similar, then actually I would think OMA is better because the receiver is simpler. But in general scenarios, if you want to maximize the overall system performance, you should do NOMA. And maybe this is the last slide on this topic. Yeah. Let us do a very simplified math analysis to see the same. This is a graphical way to show that NOMA outperforms OMA. This says OFDMA, but it is in general OMA. Maybe I'll correct it right away. So let us mathematically understand this benefit that NOMA provides. And see, this is how people write papers that get accepted at some good conferences and journals. Okay, you have the equations in front of you, and you simplify it down to the maximum way that you can, and then try to show what you want to show. Basically, you already have a pre-established goal that you want to reach, and you willy-nilly, one way or other, you just keep on hammering the equations until they become so simple that they tell you what you want them to tell you. Okay, so I mean, okay, maybe I'm trivializing this, but you will see that there is a lot of simplification that is happening here, but at the end, you will get the message. First, we'll do NOMA. And again, remember, we are simplifying tremendously. So we are going to assume that the SNR for user 1 is very high. This was the expression that we got for the rate of user 1. But if we say that SNR is very high, 1 over that becomes nearly 0. So we can ignore it. If we ignore it, then we are just left with this beta 2 divided by beta 1 term, which is same as this. If we do apply the same analysis for user 2, then we are again assuming that even SNR for user 2 is greater than 1, so we will ignore this +1 factor, and so the capacity becomes just this amount. So what is the overall system rate, R1 plus R2? It is, sorry, there is a typing mistake here. It should be log 2 of 1 plus beta 1 over beta 2 plus log 2 of beta 2 times gamma 2. Basically, summation of these two logarithms. But logarithm summation is same as the product of its terms inside the log function. And so once I multiply this term with this, I just get this value, right? Beta 2 times gamma 2 appears here. And then beta 2 times gamma 2 times beta 1 over beta 2 gives me beta 1 times gamma 2. Gamma 2 is common factor, I pull it out, then I get beta 1 plus beta 2, but that is equal to 1. And so I just get log base 2 of gamma 2. So the overall system throughput is pretty much determined by the SNR for user 2. What is SNR for user 2? Remember, user 2 is closer. And so its SNR is going to be pretty high. So we are going to get a pretty good SNR, pretty good overall system throughput. In contrast, in OMA, if we assume that the overall bandwidth is equally partitioned, then we get this type of expression. And now, remember, gamma 1 is pretty small compared to gamma 2, so we can ignore this first term. Basically, our overall system rate is going to be determined by the rate that we are giving to user 2, the stronger user. And that is going to be roughly about half of what we get for NOMA. So this is a simplified math that shows ultimately what we wanted to show, that the NOMA rate, overall system rate in NOMA can be pretty improved, pretty significantly improved compared to what you can get in OMA. Okay, so I'll take a break here and we'll resume after a few minutes. Okay, so let us continue. So now we are going to look at some of the research topics for the NOMA. And a lot of the times our focus will still be on the forward link. Okay, so let us continue there. Okay, so the first area of research in the NOMA community is about how to do the power domain NOMA. One way is to say that if I have 100 users in the cell, I'm going to do the power domain multiplexing of all those 100 users, and then the user which is the farthest away, user 1, that user receiver is going to be pretty happy because all that it has to do is SUMF. But I mean, user 100, that guy is going to get pretty swamped because now it has to do SIC of other 99 users. And that becomes pretty impractical, especially if you consider that in 5G, a lot of these user terminals are not even terminals. They may be just some simple sensors. we cannot ask them to do heavy duty computations. And so what the researchers have proposed is a hybrid of NOMA and OMA. Hybrid NOMA doesn't give the same performance as NOMA, but it solves this computational problem. The idea is very simple. Okay, when you take up some new research topic, you hear some fancy name like hybrid NOMA and all that. Your tendency is to get intimidated by it, but actually it is pretty simple thing. All that they do is break the users in groups or clusters, and so you will see a lot of papers in the literature that talk about grouping or clustering design with hybrid NOMA. What is this idea? It is just that you make sure that each group has only small number of users, sometimes only just 2 users. And you do OMA across the groups, and then inside the group you actually do NOMA with SIC. And within the group, if you have only 2 users, you are back to what we did just now. So that is the idea of hybrid NOMA. It's hybrid of OMA. Intergroup multiple access is OMA, intragroup is NOMA. So what are the research challenges? Well, a lot of them have to do with how to do the groupings. If you have 100 users and if you want to group them into clusters of 2 users, then you are looking at 100 choose 2 possibilities, which is a lot. If you want to do groups of 3 or 4 users, then the number of combinations even become bigger. And you don't want to just randomly throw them into different clusters. You need to have some principled manner, some algorithm by which you do this grouping. So how to do this grouping, how to decide how many users you want to put in a group. You do the grouping, but then you have that grouping, suppose, is happening at base station. How do the users know which group they are in? If the user's channel conditions are dynamic, they keep on changing, then how frequently you should update these groupings and so on. So those are the research problems. I'm giving you a very high level view of it. There is a lot of work that needs to be done. Some of it has been done, and that is in the literature. But otherwise, I mean, all of these topics that we are looking at, they are ripe for system level research. They are ripe for you to get a nice paper out and get your degree, maybe even PhD degree. Okay. The other research topic relates to evaluating the probability of failure of SIC. Now, I think most of these research topics I have only 1 slide. Here I may have 2 slides. I don't know. But this is a little bit of a subtle topic. Okay, I want to give you a flavor of it. But I mean, obviously it will be again scratching just the tip of the iceberg. But even to get to the tip of the iceberg, you will have to stay with me. This might be little involved concept. The reason why I'm saying that here there is a little bit of a thought required is because unlike the return link, on the forward link, if I'm looking at, let's say, user 1, then its data rate has to be formulated at 2 different locations. This goes back to, I think, what I have mentioned earlier, that there are, with 2 users, there are 4 power levels that we are dealing with. The 2 users power level at user 1's location and 2 users power level at user 2 locations. Alternatively, for user 1, there are two power levels that we should be aware of from a system perspective. User 1 power level as it is received at user 1 and user 1 power level as it is received at user 2. And therefore, correspondingly, there are two different rates as well, because rates are just logarithms of the power levels essentially. And so the rate of user 1 that we have defined in the earlier slide is given by this formula. This is the rate as it applies to user 1 location. But that user signal is being received at user 2 as well. And so it is the same formula except gamma 1 gets replaced by gamma 2. Okay? Let us go back to that formula that we had. So user 1, its rate at its own location is given by this equation. H1 squared beta 1 ptx is the power that it receives. H1 beta 2 ptx is the power of user 2 that it gets, plus the noise. And so this is the rate that we have defined for user 1. This is the SUMF rate. But at user 2's location, it is the same exact formula except H1 gets replaced by H2. If I do that, then the only thing that changes is that this beta 1 times gamma 1 becomes beta 1 times gamma 2. Only thing that happened is H1 got replaced by H2, and so gamma 1 became gamma 2. Does it make sense? Bhavesh, what do you think? Yes, no?
Yes, sir.
Okay, so that is what we are saying here, that user 1's rate at user 2 is given by this equation. Now, actually, I would say that this R12 is, in fact, more important, maybe more than even R1. Why is that? It's because, remember, the base station is transmitting the data for user 1 at rate R1. This is the rate R1 that the user 1 transmits. The user 1 data gets transmitted at. This R1 is the one that we have plotted in those 3 diagrams that I just showed you. So base station has done its job. It is sending the data at that rate R1. Basically, if you think of it as water pipe, the base station has turned on the valve and the water is flowing at certain speed for user 1. But now, if that water flow is greater than R12, then the SIC cannot be done at user 2. Because remember, user 2 does the SIC, and for that SIC to work, what has to happen? The data rate of user 1 has to satisfy the information theoretic limit. But the information theoretic limit at user 2 is this. It is not that. And so, for the information theoretic limit R12 to be satisfied, user 2 so that user 2 can do SIC, so that user 2 can decode user 1's symbols error-free. The rate at which the user 2 gets the stream of user 1, this R1, has to be less than R12. So this is the argument that you will have to wrap your arms around. Slightly involved. Arushi, does it make sense to you?
Yes, sir.
Okay. So I'll assume that you have understood this. If not, it's fine. Some of this detailed concept, first time you are presented, you may not be fully confident that you have fully grasped them, but if you chew on it on your own a little bit, I think you will get it. Okay, so now we are going to generalize this, that if I have capital M users where the indices are ordered such that user 1 is always farthest away, user 2 is next far away person, and so on, then the rate at which the base station transmits the information for mth user is given by this equation, first equation. But the rate at which user j, where j is greater than m, user j can decode user mth data is this rate. Okay, who has not spoken? Kishan, why do you think I'm taking j greater than m here?
So we are taking like a near user who is nearer to the base station.
Yes. Why? When I'm talking about mth user rate, why am I worried only about what rate user j sees, what rate user j is able to decode? But there I'm looking at j only greater than m, not j less than m. Why is that?
So they don't like users which are far away than jth user don't affect that much.
Don't what?
They don't affect.
No, that is not the answer. Okay. Who wants to answer this? What is this Rm in the bracket J? We already defined it here. This is R1 bracketed 2. What is this rate? Why is it important?
So for SIC.
Correct. It is for the rate value that we have to be considering so that the SIC becomes successful. So in that context, now can you answer why we are looking at J greater than M only?
SIC will fail in that case if J is less than M.
Why not J less than M?
SIC considers the strongest component and then removes that interference due to that from the
Exactly. I think that is the answer. I didn't fully understand it, but if J is less than M, then we don't even do SIC, right? At user J, how do we perform SIC? Let's say there are 5 users and J is equal to 3. Then at the third user, the SIC is going to be performed only on user 1 and user 2. We are not going to be cancelling out user 4 and user 5. And so J less than M doesn't matter because at jth user, sorry, if user J is such that its index J is less than M, then that user J is not even going to do, it's not going to even do cancellation of that mth user signal. Right? I mean, going back to here, we are concerned about R12, but we are not concerned about R21. Why? Why are we not concerned about R21? Because the first user doesn't do SIC on 2. It just does SUMF. So it doesn't matter what is the rate of user 2 being received at user 1's location. That is the reason why we are defining Rm of J only for J greater than M. Now, let us come back to user M. User M is going to be performing SIC on user 1, user 2, user 3, up to user M minus 1. Right? In the 2 user case, M is equal to 2, and user 2 performs SIC on user 1. If it was 3 user case and M was equal to 3, then that third user will do SIC of user 1 and user 2, and so on. And so for SIC at user M to be successful, all of the rates R n bracketed M for n greater than or equal to 1 and less than or equal to M minus 1 have to be greater than or equal to R of n, where R of n is the actual rate that the base station has transmitted. This may seem little involved here, but if you understood this, then this is a simple extension only. And that is how people write the papers. They first do something simple, like this, and then they generalize it. Generalization is not that difficult usually, although once the paper is written and they directly present this generalized equation, oh wow, this is really fancy math. Actually, it is not that fancy once you get the concept. So then the next thing is that in order for us to evaluate whether at user M, the SIC will be successful or it will fail, we'll have to evaluate the probability of the event that R1 of M is greater than R1, R2 of M is greater than R2, and Rm minus 1 of M is greater than Rm minus 1. Basically, all of these requirements have to be met. Now, what is the random variable in each of this? It is this gamma values. And therefore, all of these events become probabilistic. Gamma values are usually assumed to be Rayleigh fading variables. And additionally, there is some model for large-scale path laws. Using that, you formulate the PDFs of gammas. Then using the PDF of gammas, you formulate this PDF of these functions. And then you play around with it, and you finally get the probability of SIC failure. And that right there is your MTech thesis. Topic number 3. This is not very difficult for me to convey to you. Here the question is, how are we going to determine the power allocation ratios, beta 1 and beta 2? Well, the argument is that at the base station, there is a knowledge of what rate the weak user wants, or even the strong user wants. It doesn't matter. How does a base station know that? Well, maybe some signaling has happened earlier, and user 1 has somehow conveyed to to the base station that actually the user 1 has informed the base station that it is just a sensor, and at a time it has to send only some temperature readings, and so it doesn't take too much data rate, and so base station knows that this particular sensor needs maybe only 100 bits per second. So we are assuming that that value is known at the base station. Then all we do is we plug that value in this equation where unknowns are beta 2 and beta 1. We are also assuming that gamma 1 is known. And so now we can write this rate equation in this manner. And then it's just a matter of solving a system of linear equations. The unknowns are beta 1, beta 2. And the known quantities are this 2 to the power R1 minus 1 and gamma 1. So this is just one equation in two unknowns. So that cannot be solved. But we also know that the summation has to be 1. Beta 1 plus beta 2 is equal to 1. And so now we have two equations in two unknowns, and solving them becomes trivial. And so that is how we will define the power allocation ratios. Give me a moment. My laptop battery is weak. I will have to plug it in. So I'll be back in. Okay. Now, in some papers, this is written as a benefit of yet another practical benefit of NOMA, that this beta 1, beta 2 values can be set to arbitrary precision. I mean, unlike OMA, where it may not be possible to always set the bandwidths or the time slots to some arbitrary granularity, because those bandwidths would be more or less fixed. For example, in LTE, the sub-carrier bandwidth is 15 kilohertz. And so if your data rate requirement is only something that requires only 1 kilohertz, then too bad. I mean, you are wasting remaining 14 kilohertz. So that type of practical aspects are presented as yet another small benefit of NOMA. Okay. Multi-user MIMO. So NOMA is combined with MIMO. And a typical configuration is one in which the base station has some number of antennas, and the user terminals typically have only one antenna. But if there are NR such users, then you are back to MIMO matrix, which is NR cross NT, the one that we have studied. Okay, so there are multiple research problems of MU, MIMO, NOMA. One question becomes how to order the users. The NOMA discussion that we have had so far is the SISO NOMA. And there the channel gains are scalar values. They may be complex valued, but they are still scalars. So it is possible to order the users by taking the magnitude square of those complex numbers. In MIMO, when the user channels become vectors, then it is not very clear how would you order the users. And remember, user ordering is needed so that SIC can be organized. So one solution is that the users have to feed back the observed SNR to the base station. Again, this is on the forward link. The other is that suppose if the base station knows the location of the users, sometimes the users during the registration process have to inform the base station their GPS position. Then the base station can simply assume that the users which are closer have a stronger channel, which may not be always the case if there is a lot of fading. But anyhow, so that is one way the ordering happens. It is not based on the actual channel coefficient, but rather based on some other metrics. Now there is another interesting aspect of NOMA with MIMO. If you consider just the simple MIMO, and if you take two users who are having similar DOA, direction of arrival, at the base station, then in the context of MIMO, this is considered to be bad. And this you would know based on the earlier studies that basically if the columns of this matrix H become similar, which is the case when DOAs are similar, then the interference cancellation becomes difficult. Especially the linear interference cancellation, the decorrelating zero forcing detector may not even work because the correlation matrix R becomes non-invertible matrix. But actually, in the NOMA, that is fine because that situation becomes like a SISO NOMA. In some literature, it is called some principle of quasi-degradation. There is some degradation that is happening because of this correlation, but it is not real. Actually, SIC can benefit from this. So there are some diagrams that are drawn. Maybe I should project those figures here. Okay, so are you able to see the screen?
Yes, sir.
Yes, sir.
Okay. So this is the MIMO-NOMA diagram. And what is happening is that this base station is talking to 4 users. So there are 4 NOMA users. And it is forming the beams using the MIMO method. But what is happening is these beams are formed such that user 1 and user 3 fall in the same beam, and user 2 and user 4 also fall in the same beam. In context of MIMO only, this is a big problem, because MIMO wants to separate out these users in spatial domain. But here it is obvious that user 1 and user 3 are not separable in the spatial domain. They are inside the same beam. But NOMA is actually happy. Why? Because first of all, remember those groupings and clusterings in the hybrid NOMA/OMA? That grouping has happened naturally out of this beamformer itself. And then within a particular beam, if it was simple MIMO, there's a big problem. But with NOMA, it's actually a nice situation where you can do power domain NOMA and separate out user 1 and user 3. Okay, so that is the main idea behind this MIMO combined with NOMA. There are some details. One is, what if the base station doesn't know the MIMO channel matrix? Then basically it is the user terminals which will first have to do some type of beamforming to suppress the intergroup interference, and then apply the NOMA SIC to do the intragroup detection. On the other hand, if the base station knows the channel matrix, then it can do transmit side precoding, so that the intergroup interference is eliminated right from the base station itself. We have studied the transmit side precoding techniques. It can be the zero forcing, or it can be even simple SUMF precoding. But some precoding base station can do if it knows the channel matrix. And then it becomes a simple case of just the classical SIC NOMA at individual user terminals. And then there is one more topic. I mean, there are many other topics, but one other topic that I will mention here regarding MIMO NOMA is that remember, NOMA techniques work well when there is a power difference between the users. But what if the different users in a group do not have a lot of difference in their channel conditions? Well, one technique that is being proposed is that using MIMO, the base station will form a beam. Let us say the beam will be directed towards user 2, and user 1 will have pretty low gain of that beam. And so although both user 1 and user 2 are actually at the same distance or similar distance from the base station, after this MIMO transmit beamformer, it will be as if user 2 has become very close to base station and user 1 has become very far. And so now the SIC will work pretty well. So these are not some deep concepts. These are some practical, street smart type of approaches. But yeah, I mean, these are some good ideas, although they are not conceptually very deep. They get the job done. One more thing, NOMA actually can be leveraged to do cooperation among the users. So cooperation diversity, cooperation relaying, all of these are also big buzzwords. A lot of research has happened independent of NOMA, just cooperative user diversity and so on. Basically, cooperation means that one user helps out the other user. It is not only the base station which sends the data to a particular user, but some other user also sends the data to that user. The reason why NOMA kind of gels well with this cooperation idea is that in the forward link especially, the user 2 already has the information of user 1. It's kind of an integral part of the NOMA technique. In the traditional cooperative diversity or cooperative relaying, there is a need to put in a special design so that one user can act as a relay for the other user. Well, in NOMA that happens naturally. It's kind of an integral part of the NOMA scheme itself. That is because user 2 does the SIC, and in that SIC first step, it actually gets user 1 information bit. So the idea is that instead of just sitting with that information bit, or more to the point, throwing those information bits of user 1 away, user 2 can cooperate with user 1, and it will say that I will send you the bits that I have decoded. So user 1 will now get two sources of information. One directly from the base station, the other, the same information it will get from user 2. Whenever you get two copies of something, your estimation and detection becomes better. If not anything, you can just average out these two different measurements. Or you can do actually better than just simple averaging. You can do MMSE, for example. So basically, user 1 performance improves. And remember, user 1 is the weak user. He is the user which is far away from the base station. And so if we can improve its bit error rate, that is actually pretty important. In addition, there is a kind of a detailed benefit of using NOMA to do cooperation diversity is that with NOMA, you need only 2 resource slots. First resource slot is used by base station to send the forward link signal to both the users. And the second resource slot is needed by user 2 to send the decoded information of user 1 to user 1. So you need 2 resource slots. Now someone can argue that you can do the same exact cooperative diversity even with OMA. Yes, the answer is yes, you can do it with OMA. The only benefit of doing it with NOMA, or actually 2 benefits of doing it with NOMA, is that NOMA user 2 anyhow extracts the information of user 1. In OMA, you will have to make an additional FPGA, for example, that can, at user 2, it will not only decode its own information, but it will also decode user 1's information. So there will be some additional design needed at OMA receiver for user 2. But then, in addition to that, more significantly, with OMA, you will need 3 resource slots. instead of 2. First resource slot is for base station to send signal to user 1, second to user 2, and third for user 2 to send the data to user 1. And so overall spectral efficiency of NOMA becomes better. Okay. Let me try to show this by this diagram. So this is our user 2, and this strong solid lines are the direct transmissions, and this dotted line is the cooperative transmission that user 2 sends towards user 1. Okay, I think I have one more item. NOMA with millimeter wave communications. Now here, the argument for NOMA actually becomes slightly weaker, but still the researchers are saying that the NOMA can be applied even with millimeter wave. Why do I say that the argument for NOMA becomes weaker? It's because NOMA's main selling point is that it increases the spectral efficiency. Remember all those two-dimensional diagrams that we were looking at? The main message is that overall system level capacity for spectral efficiency improves with NOMA. When is spectral efficiency an important metric? It is important when the system is bandwidth constrained. There is not a whole lot of bandwidth available. That is when spectral efficiency becomes the metric of focus. And that is obviously the case for the 3G or 4G systems, where the bandwidth at the L band or S band is pretty occupied. Millimeter wave goes at higher frequencies, but there currently at least there is a lot of bandwidth available. It's like if you want to build a big house in downtown Mumbai, then you have to be a big industrialist to be able to do that. But the same big house, if you want to build in the middle of a desert, then, I mean, who cares? You don't need a lot of money because the land is very cheap. So at millimeter wave bands, there is a lot of spectrum, and there is a lot of spectrum. Spectrum efficiency is not that much important. So why NOMA would still make sense? Yeah, overall, NOMA may not be as much needed at millimeter wave, but in 5G, if you're talking about providing high data rates in some crowded arena, or really very high data rate technologies such as holograms, there, even if you have a lot of bandwidth, you will soon run out of it. And that is where NOMA can come to the rescue. And then the second idea is that at millimeter wave, the beams that are formed are very thin, very narrow beams. And then this other aspect that we were looking at, it becomes very common. Basically, this type of user clustering becomes more and more pronounced because these beams are becoming narrower and narrower. And so the clusterings become more and more refined in some sense. All the users that fall inside one very thin millimeter wave beam, they are automatically included as the intra-group NOMA. Okay, so that is all. The seventh topic is about the transceiver algorithms. And there are multiple techniques, LDS, SCMA, MUSA, SAMA, BDM, IDMA. All of these techniques, we will kind of do a review of it very briefly at the beginning of next lecture. And then we will get into the underlying idea, which is a message passing idea or belief propagation idea that we will study in the context of LDPC codes, but then we will see how it can be applied for various NOMA architectures. Some of these techniques are not power domain algorithms. They are not power domain NOMAs, but some of them may be kind of utilizing the differences in the power levels to do the interference cancellation. They may not also be directly the successive interference cancellation algorithms. In fact, the interference cancellation will work more using the message passing approach. But we will study that as pretty much the last final main topic of the semester in the next week. I will briefly review some of these papers. I think this paper we have already seen, some of the diagrams we have already seen. This diagram is something that I want to very quickly show to you, that this shows the outage probability, basically the probability that SIC fails, or maybe the user data rate is not getting satisfied. What this diagram shows is that if you do not do cooperation, then that outage probability is pretty high. But if you do cooperative NOMA, then you are at this blue colored bowl where the probability of failure becomes much less. Maybe from 1% it becomes 0.01 or 0.01001%. So this diagram shows the benefit of doing cooperation with NOMA. This is one nice paper. There are several other papers that I will put up in our Google Classroom. The same 3 or 4 papers that I have mentioned as references for today's lecture. And you can take a look at it on your own. Okay, one last thing I want to mention is that today Joel and Anudeep are going to be presenting their MTech Stage 1. On Friday, Kishan and Divya and Bhavesh will be presenting their MTech Stage 1. I would like you to be there if you can be there. If you have some other commitment, you don't have to be there, but otherwise attend those presentations. I think you will benefit from them. The content of the presentation, the topic is very much aligned with CT509. Okay, so that is all from me for today. If you have any questions, let me know. Otherwise, I will see you hopefully today afternoon and on Friday afternoon again, but then otherwise on next Monday.